In this video, we're going to look at one last application of these double angle identities, and we're going to use them to do some integrals that we've not integrated before. Okay, so let's say, for example, let's start with example 9. If you were asked to integrate cos squared x with respect to x, unfortunately what I've seen a lot of people do over the years on this one is you think about it as cos squared, and then you try and integrate it as a bracket to a power. You know, you might think, oh, I know, add 1 to the power, divide by the new power. What else could we do? Oh, let's divide by the derivative minus sine. I mean, it's just complete nonsense. Okay, do not start doing it as a bracket to a power. That, remember, bracket to a power, the bracket to a power technique only works for a linear function. When we're integrating, these shortcuts have to be for linear functions. If it's not linear and you're trying to integrate, something different's going on. If it was not linear, you can differentiate because you can use the chain rule. But if it's not linear and you're trying to integrate, do not start doing these shortcuts for integration. They don't work. Okay. So notice I've highlighted it as well. You probably want to highlight it in your notes. Like, if you're asked to integrate sine squared or cos squared, you have to realise that you're going to use the double angle identities. All right. So what I would do is, first thing I'd do is write the identity down. If you're ever going to use the identity, write it down. So we know that cos 2 theta, let's use the one with cos squared in, so that'd be 2 cos squared theta minus 1. And if we rearrange this identity, we can get an expression for cos squared. Okay, so add 1, cos 2 theta plus 1, then divide by 2, and that would give me cos squared theta. Okay, so instead of integrating cos squared, which you can't integrate, you're going to integrate a double angle version instead. Okay, so instead of cos squared, we could write it as cos 2x plus 1, all divided by 2. So I'm going to take that outside as a half. Remember, tidy up your integrals as you go. If it's all being divided by 2, 1/2 outside. And notice now we've got something that we can integrate. We've just got to be careful. It's been a while since we've done this. Cos integrates to positive sign. Okay, so that would be 1/2. Cos would become sine 2x. Now the coefficient is 2, so we can use a shortcut when we divide. We integrate, we divide by the coefficient, so that would be a half. Notice I put a big bracket around because this is all being multiplied by half, and then the 1 when you integrate becomes x. Don't forget your plus c, and then just tidy it up. Multiply it out, we get a quarter. Sine 2x plus a half x plus a constant. Okay, next example is example 10 from the booklet. We've got limits on this one, and we're trying to integrate sine squared of 2x. You might see the 2x and think, oh, double angle identities, but the reality is, like, the only reason we use the double angle identities is when you've got an inconsistent angle. Like, that's, you need to just look at that and say, I'm trying to integrate sine squared. The angle inside doesn't matter, okay? So this is exactly the same as trying to integrate sine squared of some angle. We'll worry about the angle later, okay? So how would I integrate sine squared? Well, I can't integrate sine squared, but I can use this double angle identity. Okay, write the identity down first. So we know that cos 2 theta is the same as 1 minus 2 sine squared theta. Rearrange to get sine squared because we're trying to integrate sine squared. If I rearrange this, 2 sine squared would be 1 minus cos 2 theta. So sine squared of an angle I know is 1 minus cos of double the angle, all divided by 2. So now we can look at what we're actually trying to integrate. We're trying to integrate sine squared. Now our angle is 2x. So instead of theta, the angle we're working with is 2x. So let's adjust this identity. Sine squared of 2x is equivalent to 1 minus cos of double the angle, so that would be 4x. If it's theta, it's 2 theta, we're working with 2x, so it would be 4x. All divided by 2. So that's what we need to integrate. So this original integral that we're being asked about is the same as integrating 1 minus cos 4x, all divided by 2, take the half outside, with respect to x. So it's minus cos, and we integrate anti-clockwise, so it's the negative sign. 1 integrates 2x with respect to x. Negative cos, still negative sine. 4x, and we're integrating, so don't forget we divide by the coefficient when we integrate. Okay, our limits are pi over 12 and pi over 24. So let's just tidy this up and see what we get. Okay, so if we sub our limits in, I'm going to leave the half outside for now. Just be careful with our brackets, everything's going to be multiplied by half. Sub our pi over 12 in, so that'll be pi over 12 minus a quarter. Sine. Now, if you're going to do this on your calculator, just be careful. Okay, I'll show you. We need to do sine of 4 lots of pi over 12. Now, if I type this in, I think it'll actually give us the wrong answer. Let me just check, make sure we're in radians, obviously. Okay, so we need to be in radians. And then I do sine of 4x, which is pi over 12. Oops. You can tell I don't use these very often, I'm doing that. So 4 times pi divided by 12. Let's just see what that gives us if I type it in like that. Yeah, that's not right. Okay. So why did the calculator not give me the right answer? We need to do sine of 4 lots of our angle, and notice what the calculator's done. It's just done sine of 4, and then times the answer by pi over 12. You need to, whenever you're doing, it's a bit of a design flaw on these calculators, whenever you're typing into a trig, trig function to figure out what the angle is, you need to make sure you bracket that angle. Okay, so it'd be sine of 4 lots of pi over 12. And that gives me the correct answer, which is root 3 over 2. Okay. Another way of doing it, you could do it in your head when you get used to this, like 4 lots of pi over 12 is pi over 3. And that's one of those common ratios, it's just 60 degrees. And I know sine of 60 is root 3 over 2, which is why I knew that other answer that we got was wrong. Okay. And then for this next one, you need another bracket because we're subtracting when we sub the level is in, so it'll be pi over 24 minus a quarter. For this one, pi over 24, again, if you want to put this in your calculator, just make sure you have a bracket around the angle. 4 lots of pi over 24. Okay, so that's going to give us pi over 6. And again, that's going to give us a nice answer because pi over 6, if we do sine of pi over 6, we just get a half. It's the same as 30 degrees. Okay, so let's tidy this up. We've got a half pi over 12 minus a quarter times by this. Now this is root 3 over 2, so that'll be minus root 3 on the top over 2 times by 4, so that'll be over 8. Minus, I'm going to keep a bracket, pi over 24 minus, okay, if we do sine of pi over 6, we get a half, so that'll be minus 1/8. So we've got pi over 12 minus pi over 24, so that's 2 24s minus 1 24, so that'll be pi over 24. Minus root 3 over 8 plus, because minus minus becomes plus, so plus 1/8, so that would be 1/8 minus root 3/8. So we could write that like that. And then if we expand out by the half, we get pi over 48 plus 1 minus root 3 over 16. I'm just going to check that's the same as the answer in the booklet. So they've actually split it up, but it's the same thing. Like they've just written this as two separate terms. So that's 1/16 minus root 3 over 16. I'm going to leave it like that. Okay. Okay, so I'm going to do one bonus example, which isn't in the booklet, because this is another important one. It's not sine squared, it's not cos squared, but what we've got is we're trying to integrate sine times by cos. So let's think, is it something that I know it's integrate? No, it's not something that immediately comes to mind. Could we try parts? Could two things multiplied together? No, you don't really ever, very rarely want to do parts when it's two trig functions multiplied. Definitely not in A-level maths, you don't want to be doing parts if it's two trig functions multiplied together. Like remember, we do parts if it's like x sine x. So this doesn't look like a parts question to me. Normally when we get two trig functions multiplied together, it's a substitution. But there's no obvious substitution that would work. I mean, there is actually a substitution we could do, but let's just pause for a second and think, hang on a minute. We know these double angle identities, 2 sine theta cos theta is the same as sine 2 theta. So this would just be the equivalent to integrating sine 2 theta d theta, which is something we can integrate. Sine integrates to minus cos. Divide by the coefficients and add your constants. Okay, that should help with one of the questions in the booklet, guys. Alright, so that's us done on the A-level maths trig content. Hopefully the videos have been useful. Obviously, keep an eye out for the work solutions and let me know if you need any help. Okay, thank you.